Welcome back. Let's start today's Q&A session. So just as before, if you have questions, please come forward and ask questions to our lecturers.
First, I have a question about resurgence. There are, for example, in instant partition function, there are some cases that we can know only first few coefficient of the series, not a full coefficient. Then, in that cases, can we perform some resurgence techniques, such as resummation?
Can you be a bit more specific?
If we know just the first few coefficients of the series, then can we borrow resummation that series?
Well, you can, but you won't get very high precision.
High precision.
You won't get very high precision if you only have a few terms.
Okay, thank you. And can I ask another question to integrability? Can you consider a Yang-Baxter equation for more than 2 dimensions?
Yes, well, there is a thing called tetrahedron equation, which basically describes the scattering of rigid string in 3 dimensions.
3 dimensions.
But this is not the scattering of the particle. So there is no natural realization in quantum field theory. You can write down the equation and then you can try to find the answer, but I don't know any realization in quantum field theory.
Okay, thank you.
I have one question to Dunne, and this, for example, real-time correlator, out-of-time correlator. That such kind of there is many approximation, and some calculation is only valid up till scrambling time, because beyond that it's perturbation breakdown. But by using the resurgence, is there some study understand beyond some long time behavior?
Yes, there are several groups trying to implement this numerically for non-equilibrium problems.
Analytically, is there some more understanding?
It should be possible. I haven't done it myself, but it's clearly designed to handle exactly these problems.
Mm-hmm. I see. Okay.
So there are explicit examples on the lattice now, calculating simple out-of-equilibrium problems in quantum mechanics, doing it non-perturbatively.
Okay.
You can look at some of the references if you like.
Also, black in the gravity, like in the black hole background, is there some study?
Not yet.
Not yet. Okay. And I have a simple question to Komatsu. So today you talk about the ON, the vector model in 2D boson. And in this derivation, whether it's boson or fermion really doesn't matter. In 2D, because bosonization, I think it's similar. But is there any room for this kind of to distinguish them, or it does not necessarily distinguish?
Okay, so well, actually, the analysis that I described today applies both to bosons and fermion, because I basically only talked about the matrix structure, and which is governed by just ON symmetry. And in fact, I talked about ON model, whose underlying Lagrangian is bosonic, but sorry. Okay, but the analysis is also applicable to what's called Gross-Neveu model, which also has a ON symmetry, and the matrix structure of the S matrix is actually exactly the same. So the only difference is in the overall coefficient.
Okay, thank you.
So in your lecture, the I alpha and sorry, the alpha and act on the wave packet.
The wave
wave packet. The FP is transformed to the FP plus I alpha n and p power of n. But why power of n is displayed in the?
Okay, so it's because of my assumption about how those higher charges act on the plane wave state. I assume the existence of higher spin conserved charges whose action on the plane wave state with momentum p is to just like multiply p to n. And I exponentiated that generator and then act on the plane wave states. That's why you get p to n.
Thank you for this answer.
So I have sort of naive question about this integrability. So I mean, is there any way to define integrability other than S matrix? Like, for example, I have seen people saying about integrability of some gravity model and all these things. So I mean, what is the notion of integrability beyond the S matrix thing?
Okay. So I guess when you said integrability of the gravity, I think in that case, I think what people have in mind is the integrability of classical gravity equation, like the equation of motion. And so today I mainly talked about quantum integrability, which has some consequence on the S matrix. But you can also talk about the classical integrability, and essentially it's related to some techniques of solving the classical nonlinear equation. And I don't have clear-cut answer for general classical integrable systems, but for the case of nonlinear sigma models, you can consider like a various target spaces. Then people know that if the target space belongs to what's called symmetric coset, then there is a way to rewrite the classical equation of motion of that nonlinear sigma model into some nice form. And if you have that nice structure, which is called the lax formalism, if you have that lax formalism, then you can actually kind of construct various solutions. There is a kind of systematic way of constructing various solutions. And in addition, that lax formalism allows you to construct infinitely many conserved charges, classically conserved charges. So in that sense, that notion of classical integrability is also related to what I talked about today, but it's not exactly the same.
But for example, quantum integrability, I mean integrability of quantum field theories. So like, so for example, if I defined a quantum field theory on a manifold, where like S matrix doesn't have any useful notion of S matrix, so in that case, can I say anything about integrability?
Okay, so I don't know the statement about general compact manifold, but there is something you can say about the theory on a torus. And of course, on a torus, you cannot define the S matrix. Or, well, let's first consider cylinder and then ask what is the energy spectrum on the cylinder. I mean the 1 plus 1D. And of course, in this case, you cannot define the S matrix because the space is compactified. But actually, there is a method to calculate the energy spectrum on the cylinder using the data of the S matrix. So using the data of the flat space, you can actually compute the energy spectrum. That's called thermodynamic Bethe-Ansatz. But I don't think I will have time to talk about it. But there is such a formalism.
So for ADS case, does this million amplitudes,
Okay.
in terms of million amplitude, can I define integrability or something?
Wow, yeah, that's an interesting question. So yeah, you're asking, for example, what happens if I put integrable quantum field theory in ADS2? Is there any nice notion of integrability? Yeah, in the last few years, I've been discussing that question to several people, but I don't know the answer yet.
I have a question to Komatsu. I think you mentioned in the lecture the double pendulum as an example of chaotic behavior with integrability. I wonder whether integrability imposes any chaotic bound, non-trivial way.
I don't know. Well, if it's classically integrable, it's typically not chaotic. So yeah. So it seems to me they're kind of exclusive to each other. Yeah. So I don't know any like a classical theory in which you can say something about chaotic motion using the notion of integrability.
I see. Thank you.